How subjective memories are realized in TGD-inspired theory of consciousness. We remember our conscious experiences, also as re-experiences, and not as learned, often unconscious behaviors that reduce to associations, according to neuroscience point of view. The information of the conscious experience, if determined by the quantum jump, must be about the initial and the final states of the quantum jump, and the transition between them. In the standard ontology of quantum theory, it can't be represented by the final state of the quantum jump. According to the standard theory, quantum states are three-dimensional time-equal constant snapshots of time evolution and do not remember anything about the previous quantum jumps. No subjective memory. In TGD, the zero-energy ontology, ZEO briefly, combined with holography equivalent to holomorphic vision, suggests a universal mechanism of memory storage and recall. The slight non-determinism of the classical field equations, determining the space-time surface as a minimal surface, implies that quantum states are superpositions of space-time surfaces analogous to four-dimensional Bohr orbits for free surfaces interpreted as particles. State function reductions, SFRs briefly, occur between these states and the information about the initial state in three-dimensional sense and about the transition to the final state in three-dimensional sense is coded to the Bohr orbits associated with the final state. This allows to code the information to the final state, quantum state. The slight non-determinism in turn makes possible memory recall in ZEO. The proposed mechanism is universal and applies also to matter which is usually regarded as dead, because it looks dead in the timescales of our perceptive abilities. This justifies the notion of the four-dimensional brain. In the sequel, the notion of memory is discussed from the points of view of computer science and neuroscience, of quantum theories of consciousness, and of TGD-inspired theory of consciousness. Subjective memory as a basic problem of theories of consciousness. Memory as a challenge in computational and neuroscience approaches to consciousness. Computers completely lack subjective memory if they are what they are believed to be, that is, they obey the Turing paradigm. Computers are also believed to be deterministic, either in the sense of classical physics or of statistical quantum mechanics. Since non-determinism is a basic aspect of conscious entities' free will, computers are expected to lack conscious experience. One can, of course, challenge the Turing paradigm. In neuroscience, memory is often interpreted as mere learned behavior. This view is a remnant of behaviorism. Associations provide a mechanism of memory, and association is also the basic mechanism of now fashionable large language models. This interpretation does not explain at all the episodic experiential memories that we also have. Some of us have very intense sensory memories. All of us have dreams involving memories, sensory memories, and the electric stimulation of the parietal lobes of brain can induce lively sensory memories of the past events in anyone. So, memories must be stored in some sense. This is the first challenge. In neuroscience, the finiteness of the memory space becomes a basic problem. If memories were carved in stone, a large number of stones would be needed, and the number would be increasing all the time. It might be natural to give up some memories, most naturally the oldest ones. Computationalists would say that new data is written over the older data. What happens is just the opposite. The last memories to disappear are the childhood memories. The strong emotional content of these memories is certainly one reason for this. They are also remembered many times for this reason, and this produces many copies of them, which makes it easier to recall them. This might be used as a neuroscience explanation for their stability. The understanding of reading of memories, that is, having a conscious experience, providing information about the memory, remains an unsolved challenge in neuroscience context. This would require genuine theory of conscious experience. Memory is a key challenge for quantum theories of consciousness. Any theory of consciousness, including quantum theories of consciousness, should be able to explain the basic mechanism of conscious memory. A basic element of subjective memory is its temporality. Its contents correspond to the events of the past, sequences of discarded events. An attractive idea is that by their non-determinism, which is a basic behavioral feature of conscious entities, quantum jumps determine the development of consciousness. Subjective memory recall would therefore represent information about the previous quantum jumps. The outcome of quantum jump should represent information about what was experienced in the past. The information about the conscious experience, if associated with quantum jump, should be about the initial and the final states of the quantum jump, and also the transition between them. It should be, however, encoded into the final state of the quantum jump. In the standard ontology of quantum theory, this is not possible, since quantum states are identified as three-dimensional time equal to constant snapshots of time evolution. They do not remember anything about the previous quantum jumps. Therefore, theories of consciousness based on standard quantum mechanics can't explain subjective memory. For some reason, this fact seems to have been overlooked. The understanding of subjective memories is therefore a hard challenge for quantum theories of consciousness. There are some guidelines concerning the understanding of subjective memories, if one accepts only the statistical view of quantum theory. A natural proposal would be that in some sense the characterization of quantum statistical time evolution corresponds to some kind of Markov chain, sequence of events. A stronger condition would be that quantum states are replaced by sequences of three-dimensional quantum states. This would require a failure of strict determinism, but standard quantum theory does not allow this. The failure of strict classical determinism is, however, a valuable guideline, and would mean that quantum states are in some sense slightly four-dimensional, so that the brain would be slightly four-dimensional. The zero-energy ontology of TGD indeed predicts this. Quantum states are superpositions of four-dimensional classical space-time surfaces, time evolutions, obeying almost deterministic holography, so that they are indeed slightly four-dimensional and analogous to Bohr orbits of three-dimensional particles. In TGD, zero-energy ontology combined with holography equivalent to holomorphic vision suggests a universal mechanism of this kind. In the sequel, a general TG-based mechanism of memory storage and memory recall will be discussed. By its universality, the proposed mechanism applies also to matter, which is usually regarded as dead, since it looks dead in the timescales of our perceptive abilities. TGD-inspired view of subjective memory. Zero-energy ontology briefly. We have memories about the conscious experiences of the past. How are these memories formed? How are they recalled? These are the basic questions. In TGD, classical physics is an exact part of quantum physics. This is something new. Zero-energy ontology suggests a rather concrete model for the classical representations of the memories, in terms of the geometry of the space-time surface. Consider first a brief summary of ZEO. The three basic notions of ZEO are causal diamond, zero-energy state, which can be also seen as a pair of ordinary three-dimensional quantum states at light-like boundaries of causal diamond, and state function reduction. Here, small causal diamond is the intersection of future and past directed light cones of Minkowski space. Space-time surfaces are located inside this causal diamond. There are two kinds of state function reductions: small state function reductions, SSFRs, and big ones, BSFRs. A sequence of SSFRs is a TGD counterpart for a sequence of repeated measurements of the same observables. In wave mechanics, they leave the state unaffected. This is the well-known Zeno effect. Already in quantum optics one must loosen this assumption, and one speaks of weak measurements. Something happens, but it is not very big. In ZEO, state function reductions do not affect the three-dimensional states, small state function reductions. They do not affect the three-dimensional states at the passive boundary of causal diamond, but affect them at the active boundary. This gives rise to a flow of consciousness and defines self as a conscious entity. The quantum change is at the active boundary of CD. Since the size of the CD increases, this increase gives rise to a flow of geometric time, correlating with the subjective time. BSFA is a counterpart of the ordinary state function reduction. In BSFR, the arrow of geometric time changes since the roles of the active and passive boundaries change. BSFR means death of self and reincarnation with an opposite arrow of geometric time. The CD or the active boundary increases in opposite direction of geometric time. Therefore, death and reincarnation are universal notions in the TGD universe. Falling asleep and biological death are basic examples of big state function reduction. Since TGD predicts quantum coherence in arbitrarily long length scales, the arrow of time can change in even cosmological scales, which has rather dramatic implications. The classical representation of the information of subjective memories. Causal diamond is a Cartesian product of small CD of Minkowski space and CP2. Small CD is the intersection of future and past directed light cones of Minkowski space. Zero-energy states can be regarded as pairs of three-dimensional many-fermion states at the opposite light-like boundaries of the CD. Second view of quantum state is as a superposition of space-time surfaces obeying holography and therefore analogous to Bohr orbits. This picture is made more complex by the hierarchy of CDs. There are two new phases, pairs of fermion states and superposition of four-dimensional surfaces rather than three-dimensional ones. It is essential that the holography is slightly non-deterministic. Holography, equivalent to holomorphy principle, allows an explicit construction of space-time surfaces as holomorphic minimal surfaces, and they are analogous to Bohr orbits. When one interprets free surface as a generalizer of a point-like particle or of string. Already two-dimensional minimal surfaces fail to be completely deterministic. A given frame can span several song films. This non-determinism forces zero-energy ontology. Otherwise, one would have ordinary ontology with three-dimensional surfaces as basic dynamical objects. No hope about memory, conscious memory. The failure of the strict determinism makes four-dimensional Bohr orbits slightly dynamical objects by giving them additional discrete degrees of freedom. These degrees of freedom are absolutely essential for the understanding of memory. One can speak of four-dimensional brain. The three-dimensional many fermion states at the boundaries of causal diamonds and the restriction of the wave function in the world of classical worlds consisting of these Bohr orbits to the space of free surfaces identified as the ends of Bohr orbits at the passive boundary are unaffected by the sequence of SSFARs. This is a counterpart of the Zeno effect. Passive boundary, nothing happens. A given state function reduction, small state function reduction, must correspond to a measurement of observables commuting with the eigenobservables at the passive boundary. Otherwise, state changes at the passive boundary. The simplest option is that these observables are associated with a discrete degrees of freedom due to the classical non-determinism. Quantum and classical non-determinism would be very similar. The three-dimensional states at the opposite active boundary of causal diamond are however affected in small state function reductions. This gives rise to self and flow of consciousness. Also, the size of CD increases in a statistical sense during sequence of small state function reductions. The sequence of state function reductions, small state function reductions, gives rise to subjective time correlating with the geometric time, which is identifiable as the temporal distance between the tips of the causal diamond. The arrow time depends on which boundary of causal diamonds is passive, since the active boundary recedes from the passive boundary in statistical sense. In TGD, ordinary state function reductions correspond to big state function reductions. Both big and small state function reductions are possible in arbitrary long length scales, since the hierarchy of effective Planck constants makes possible quantum coherence in arbitrarily long length scales. The new element is that the arrow geometric time changes in big state function reductions, since the roles of active and passive boundaries indeed change. Big state function reduction occurs when the set of observables measured at the active boundary of CD no longer commutes with the set of observables associated with the passive boundary. There is no other option than the change at the passive boundary. The density matrix of the three-dimensional system, characterizing the interaction of the free surface at the active boundary with its complement, is a fundamental observable. Certainly this is the case. If it ceases to commute with the observables at the passive boundary, big state function reduction is unavoidable. The degrees of freedom characterizing the classical non-determinism are crucial for memory, since they commute with the eigenobservables at the passive boundary for an obvious reason. They naturally belong to the degrees of freedom measured in SSFRs. Even other aspects of consciousness, perhaps all, might relate to this kind of state function reductions. Classical determinism and quantum determinism for cognition and consciousness in general would be closely related. The mechanism of memory recall in GTO. The view has been that active memory recall requires what might be regarded as communications with the geometric past. Active memory recall indeed requires sending a signal to the geometric past, propagating in the non-standard time direction, and being absorbed by a system representing the memory locus, part of the brain or of its magnetic or field body. In ZEO, this is possible. BFR's big state function reductions indeed change the arrow of the geometric time. The signal must be received by a system of the geometric past representing the memory. Therefore, the signal would be generated in BSFR or some subsystem in brain. The signal would be received in the quantum reticle memory location in the geometric past by a resonance mechanism, and then a second big state function reduction would take place. It would result in a response that would propagate to the future brain and received. Note that this requires that four-dimensional space-time surfaces are not completely deterministic. The findings of Minev et al. Demonstrate that in quantum optics, quantum jumps correspond to smooth classical time evolutions, deterministic, leading from the initial state to the final state. This provides a direct support for the ZEO view. The interpretation works for small state function reductions and also for the interpretation of transitions as pairs of big state function reductions, having interpretation as quantum tunneling events involving temporal change of the arrow of time. What happens is that a set of three-dimensional final states at the active boundary of some three-dimensional state is selected. This means localization in the world of classical worlds, VCV, as a space of Bohr orbits. The zero-energy state is localized so that three-dimensional surfaces at the active boundary, or CD, represent the outcome of quantum measurement. In zero-energy ontology, the zero-energy states as the outcome of the state function reduction also represents the transition to this state. This is not possible in the standard ontology. Is the conscious experience associated with small state function reductions assignable to the classical non-determinism? The sequence of small state function reductions corresponds to a sequence of geometric representations of memories about conscious events. In this way, the universe can gradually develop representations of its earlier quantum jump history to its own state. Since the algebraic complexity of the universe can only increase in a statistical sense, the quantum hopping of the universe in the quantum Platonia, defined by the spinor fields of world of classical worlds, implies cognitive evolution. The evolution is forced by the unavoidable increase of algebraic complexity. The information content of the universe increases all the time. At least memory would correspond to regions of the space-time surface where quantum jumps between the different classical alternatives are possible. These hotspots would be analogous to the frames spanning the sound film, and as quantum critical systems would be ideal seats of memories. Could also sensory and cognitive state function reductions, small state function reductions. In fact, all small state function reductions correspond to classical non-determinism. Could the classical quantum correspondence fail only for big state function reductions as counterparts of the ordinary state function reductions? In these measurements, the observables would not correspond to classical non-determinism. Memory and TGD inspired quantum biology. TGD predicts that any system can have a self, identified as a sequence of state function reductions, small ones. Therefore, there is an entire hierarchy of systems which can be conscious The question is, what level in this hierarchy does biological consciousness correspond to? In the case of the brain, the quantum-critical, slightly non-deterministic hotspots of the four-dimensional space-time surface representing the brain could be associated with DNA, microtubuli, neurons, axons, and larger structures constructed from them. Also, the field bodies are natural candidates. Gravitational Planck constant and electric Planck constant characterize the gravitational magnetic bodies and electric bodies. Their values are really large, very long quantum coherence lengths. Both DNA, microtubuli, and cell have large electric charges, which supports this electric quantum coherence. Also, the gravitational magnetic bodies of the Earth and Sun are excellent candidates for the field bodies involved, and various numerical miracles support this view. Water is essential for life. It is expected also to be crucial for our conscious experience. The proposal is that the monopole flux tubes accompanying the ordinary basic biomolecules, DNA, proteins, and so on, carry sequences of dark protons. They would provide a universal representation of the genetic code, possibly in all scales. The notion of dark DNA, realized in terms of dark proton triplets, leads to a proposal that the genetic code is realized in terms of a completely unique icosatetrahedral tessellation of the hyperbolic free space. This would be crucial for the communications based on multi-resonance mechanism as a selector of the receiver, and frequency modulation as a way to represent information. This mechanism, associated with the EEG and its fractally scaled up copies, could be essential also for memory recall. For dark photons, period and wavelength for a given energy are scaled up by this effective Planck constant. The larger the value of effective Planck constant, the longer the span of memory.